Welcome to episode 5 of Physics Calculations. Until I get a girlfriend. Today we're going to be learning about centrifugal force and circular motion. Circular motion is an interesting topic because motion involves vectors.
Oh yeah!
Vectors are always straight lines. So it's seemingly paradoxical how straight linear velocity and linear acceleration can create circular motion. So that's the central question. How can we relate linear acceleration and linear motion, linear acceleration and linear velocity into circular motion? I think the most intuitive example for circular motion is a mass on a string. So we know that the force acting on this mass is tension. So let's look at which direction that tension is going. So when the mass is here, the tension is going to the center of the circle. When the mass is here, the tension is going to the center of the circle. And when the mass is here, the tension is going to the center of the circle. So no matter where the mass is along its path of travel, its acceleration is constantly changing directions. And that's how motion can be curved.
If the acceleration is always inward, what about the velocity?
Newton's first law states if the sum of forces is 0, then velocity is constant. So let's see what happens when we stop applying a force. So it appears that the mass doesn't continue in its circular motion, circular orbit, does it? So we know that velocity is linear because that's just the definition of a vector.
Oh yeah!
So what's going on here? Well, if I stop applying inward force, the path of travel is no longer curved. In fact, it's linear and it's always tangential. It's always tangential to the path of travel. And that's the answer to the central question. How do we relate acceleration, velocity, and circular displacement? Acceleration is always inward, velocity is always tangential to the circular path of travel. This is the circular acceleration formula. A is equal to v squared over r, and it's also the answer to the central question. Let's try to do this logical conclusion thing in a sense. So if A is equal to v squared over r, what would happen if r approached infinity? Well, as the radius got larger and larger, the curvature would be less and less. And if r approached infinity, this number got larger, this number would be a lot smaller. So we can logically conclude that straight paths of travel have no sideways acceleration. And that just makes sense. So just a cool thing to think about. Logical conclusions. Another cool logical conclusion is this thing here. What is the force of tension? Remember from the Dr. Pepper thing, what's the force of tension when it's at the top of its travel and at the bottom of the travel? We know that the circular force is equal to the force of gravity plus the force of tension, right? At the top and the bottom. So if the force of gravity is constant, and the centrifugal force is constant because it's a perfect circle, then isn't the force of tension constant? No. Well, had you looked at the asterisk and read the fine print, you'd realize that the magnitude of the centrifugal force is constant, but the direction isn't. So how can we find the force of tension at the top and the bottom of the path of travel? Alright, so why don't we look at, so the force of gravity, which is represented by a squiggly line, and the force of tension, which is represented by a dashed line, must be equal to the centrifugal force, right? Well, look at this. Here, the centrifugal force, to match the centrifugal force, the squiggly constant force of gravity works alongside the dashed force of tension. But here, because gravity is always downward, this squiggly force of gravity is kind of working against the dashed force of tension. So to get the force of tension, it's it's the centrifugal force plus or minus the force of gravity. So it's kind of interesting that the string has different amounts of tension along its path of travel. Circular paths of travel occur a lot in nature and happen all around us, such as a skateboarder on a half pipe, planets around the sun, and an Indian with Ebola. Could you match the diagram with the correct forces? I'll give you a hint. Forces always act inward. All right. If you answered force of gravity, force of nature, and force of wind, you're stupid. In this case here, the force of gravity will always be pointing down no matter where the skateboarder is along its path of travel. And that's not what causes circular motion. However, the normal force always is perpendicular to the surface. And in this case of a curved surface, it's always pointed to the focal point of that circle. So, normal force would go here. In this case here, all forces act inward. That's just the force of gravity. And just like in the example with the Dr. Pepper, this is just the tension of the string. If circular motion is all around us, when will I ever need to use this formula? Well, Highway 1 connects to Highway 17. There's a ramp right here. It's a circular ramp. I think this is technically called the fishhook. I don't know if that's the fishhook or if the other loop-de-loop is the fishhook, or if the 17 to 1 is the fishhook. I don't know. But this ramp here that connects the Highway 1 to Highway 17 has a radius of about 339 feet, and the speed limit is 40 miles an hour, because we're all law-abiding, good, upstanding citizens here. So how can we find the acceleration experienced by the driver? All right, well, your hint is A is equal to V squared over R. So you just plug that in. And that's your answer, 2.7 newtons. But another thing, I want to go off on a tangent here. Tangential velocity, I'll make a joke. Tangential velocity joke, I will. No, I won't, I'm not gonna do that. Anyway, what I like to do here is follow the units. Acceleration is meters per second squared over meters. Meters per second squared over meters, it all cancels out, and you get meters per second squared. So I was wrong. This is not newtons. Newtons is force.
Oh, bro! Oh, yeah!
If you always follow the units, then you will know that the formulas that you use, the method that you got there is true. You may not get the correct number, but you will know that the path that you took is correct if you follow your units. All right, problem number 2. A pendulum is swinging 30 degrees from vertical. What is the acceleration experienced? Wow, with such little information, how can we solve this? Well, seeing how it's traveling in a circular orbit, the number that we're trying to find is this thing here, the arrow that points inward. Because although we may think that we're going to deal with forces such as that, we're not, because we know that the pendulum's y is kind of constant. It stays on the same y plane in a sense. So if this were to be an overhead view, we're trying to find this value right here. This is your hint, alright guys, this is the hint. It's on the Earth. It is on, yeah, it's on the surface of the Earth. So is that the answer, 9.81? No, that's not the answer. Again, we're looking for this direction, not this direction. I know this is a little abstract, but if only there was a formula that we can use that involved this 30-degree angle here, finding this acceleration here, and knowing that this is 9.8. Yeah, the solution is trigonometry, which is kind of crazy. It actually kind of makes sense if you think about it. I mean, imagine if there's like, this is an overhead view, right? And you're pulling in south and I'm pulling east, right? If my pole is infinitely stronger than your pole, right? If you're not pulling, then it's just going to be perfectly that direction. And the same is true if I'm not pulling and you are. If I'm not pulling and you're pulling. But if our poles are like equal in strength, then the angle would be a perfect 45 degrees. And if my pole is stronger, it'd be more like that. If your pole is stronger, it'd be more like that. So that using trigonometry to get the ratio just kind of makes sense. So this one, we don't use the a is equal to b squared over r formula. Let's just use what? Tangent and I love to follow units. The cool thing about trigonometry is that it's technically unitless, right? I mean, imagine just a normal triangle. The ratio between a meter and a meter is meter divided by meter, so it's unitless. In other words, for this side of the equation to be unitless, because this side of the equation is unitless, this needs to cancel out with this. So the meters per second on the denominator must be counteracted by a meters per second squared in the numerator. Follow your units. Alright, a race car driver is on a circular track. The circuit's lap length is 1.57 kilometers, and if it takes the driver 31.5 seconds to complete one lap, what is the inward acceleration that he experiences? Circle gaming, boys! Time to use the circle equation. Let's see. Well, that's not given. Unknown. The velocity is also not given. So an unknown is equal to an unknown. And the radius is also not given. What the sigma? So an unknown is equal to a relationship between two unknowns. That's not really helpful. Even though these aren't given, we can still use derivation. Even though the velocity and the radius aren't given. If we look at the symbolic domain, I feel like we can derive those variables. I mean, the circuit length is really just the circumference, and from that we can derivate the radius. How can we derivate the velocity? Well, we can derivate the velocity because we know the distance that it travels over time. Cool. So even though we were given we have to solve an equation with a bunch of unknowns, we could still derive some of those values to get the final acceleration. Alright, so let's perform some calculations. Alright, so we have all of our formulas, and if you just plug in length from 2 pi, we get the radius, and if you get distance over time, you get the velocity. Simple calculations, you get those numbers. Another way to think of velocity is we were given distance for each lap, and we were given the time for each lap. So we can kind of arrange it like this. We could get distance over time, which is just velocity. And with the radius and the velocity, we could calculate the final acceleration.
That will do it for today's video. I forgot to film an outro. Don't forget to dislike and report.